Introduction to the Space Elevator. The space elevator is a revolutionary concept that aims to provide a way to transport people and cargo from Earth's surface to space without the need for rockets. Unlike traditional space travel, which relies on chemical propulsion and costly launches, a space elevator would function as a continuous, reusable link between Earth and space, allowing for more affordable, frequent, and sustainable access to orbit. The idea, often attributed to Russian scientist Konstantin Tsiolkovsky in 1895, involves a tether extending from Earth's surface up to geostationary orbit, approximately 36,000 kilometers or 22,236 miles. Along this tether, vehicles or climbers would ascend and descend, carrying payloads into orbit or even further out into space. While this concept may sound like science fiction, it has captured the imagination of scientists and engineers for over a century. How would a space elevator work? 1. The tether. The key component of a space elevator is the tether, a long, extremely strong cable stretching from Earth to space. The cable would be anchored to a base station on the ground, likely near the equator, where geostationary orbit aligns perfectly with Earth's rotation, and extend upward past geostationary orbit. To keep the cable taut and stable, a counterweight would be placed at the far end, likely an asteroid or large satellite beyond geostationary orbit. 2. Geostationary orbit imbalance. The space elevator works due to a balance of forces. At geostationary orbit, the centrifugal force caused by Earth's rotation would match the gravitational pull, effectively holding the cable in place. The counterweight ensures that the tension remains constant throughout the length of the tether, keeping it stable and upright. 3. Climbers. Vehicles known as climbers would ascend and descend the tether. These climbers would be electrically powered, potentially drawing energy from solar power, wireless energy transfer, or beamed lasers from the ground. Unlike rockets, which must carry fuel to overcome Earth's gravity, climbers would only require energy for movement along the tether, significantly reducing the cost and complexity of space travel. 4. Base station. The Earth-based end of the elevator would likely be located on a mobile ocean platform near the equator. This ensures that the base can adjust to the forces acting on the tether and minimizes risks from weather events or terrestrial instability. Advantages of a space elevator. A functional space elevator could revolutionize space exploration and industry for several reasons. Reduce launch costs. The most significant advantage is cost reduction. Traditional rocket launches cost thousands of dollars per kilogram of payload. A space elevator could reduce this to mere tens of dollars per kilogram, making space travel more accessible and enabling large-scale infrastructure in space, such as solar power satellites or space habitats. Environmental impact. Rocket launches have significant environmental impacts, including carbon emissions and the release of pollutants into the upper atmosphere. A space elevator would use electric power, potentially from renewable sources, significantly reducing the environmental footprint of accessing space. Frequent and reliable access to space. Current space launch systems are constrained by weather availability and technical challenges. A space elevator would operate more like a train or conveyor system, providing regular and reliable access to space. This would open the door to space tourism, resource extraction from asteroids, and much faster space station resupply. Space exploration. With a space elevator, sending large payloads to space would become routine. This could enable the construction of larger spacecraft in orbit for missions to the Moon, Mars, and beyond, without the need to launch them entirely from Earth. Challenges in building a space elevator. 1. Material strength. The biggest challenge is finding a material strong enough to withstand the immense forces acting on the tether. The tether needs to support its own weight over 36,000 kilometers and endure both the gravitational pull of Earth and the centrifugal force at geostationary orbit. Steel, aluminum, and even advanced carbon fiber are not strong enough. A potential candidate is carbon nanotubes or graphene, both of which theoretically possess the strength required. However, current manufacturing techniques cannot yet produce these materials in the necessary lengths or quantities. Advancements in nanotechnology and materials science will be critical to overcoming this hurdle. 2. Weather and environmental hazards. The tether would be exposed to environmental hazards, including high-altitude lightning strikes, wind, and even space debris or micrometeoroids. These could damage or sever the tether, potentially leading to catastrophic failure. While localized repairs are possible, designing a tether that can withstand or mitigate these risks is a significant challenge. 3. Space debris. Space debris in low Earth orbit presents a major risk to the tether. Even small pieces of debris moving at high speeds could cut or damage the cable. Solutions like actively removing space debris or designing the elevator to dodge such debris would need to be developed. 4. Powering the climbers. Powering the climbers along the tether is another technical hurdle. While concepts like wireless energy transfer, e.g. laser or microwave beaming, have been proposed, scaling these systems up to power vehicles that can climb tens of thousands of kilometers is a massive engineering challenge. 5. Economic and political feasibility. The cost of developing a space elevator would be astronomical, likely exceeding hundreds of billions of dollars. Securing the necessary funding, whether through governments, international cooperation, or private investment, is another barrier. Additionally, the geopolitical implications of who controls access to space via the elevator will need to be addressed, requiring international treaties and agreements. Could a space elevator ever be built? While a space elevator remains a theoretical possibility, it is not entirely beyond the realm of plausibility. Significant advancements in materials science, energy transmission, and space debris mitigation would be necessary before construction could begin. The project's economic and political feasibility will also be a critical factor. If these challenges can be overcome, however, the benefits of such a system would likely outweigh the costs in the long term. The concept is being actively researched by organizations like NASA and various private companies. Some predict that we may see the first operational space elevator within the next 50 years, while others argue that the technological hurdles may delay its development for centuries. Conclusion: a space elevator represents one of the most ambitious visions for the future of space exploration. While numerous technological, environmental, and political challenges remain, the concept offers a tantalizing vision of affordable, reliable, and sustainable access to space. Should it ever be built, it would revolutionize our relationship with space, transforming it from a distant frontier into a new realm of human activity. The path to achieving this dream, however, is steep and uncertain, requiring breakthroughs in several scientific disciplines and massive investments in infrastructure. But as with many grand human endeavors, the potential rewards make the challenge worth pursuing. Thanks for watching.